Okay. You are you are part of my you are my audience. Okay.
Yes.
I have a camera that's trained on me. Okay. This camera is taking pictures of me talking to you. You're not on camera. I have done 20 videos like this.
You've done
so
what?
far. I have done 20 videos like this.
Oh, really?
20 videos like this. Now, I created these videos for the purpose of showing my grandchildren when they're old enough to care, which I have no idea what that age is, maybe in their 60s, you know?
Science won't exist.
Well, they'll say, at some point they'll get old enough to stop being concerned with perhaps themselves, narcissistically speaking, and wonder about their own ancestors. And I will be long dead. And they will go, I wonder what he was like, you know? And so there will be hopefully this archive. I will be in this archive. I will be here talking to them. Hello, grandchildren. I know you're Wesley in the middle, and then there's Tessa on one end, and Orion on the other end, and who knows if there's another one, okay? So hello, hi. Just for posterity's sake. So what I did is I started putting these videos up on the web in a place called Skillshare. And Skillshare tells me Skillshare. And so for those of you who've been coming regularly, you know that that's the word that I told you where to go to see the videos. Well, apparently Skillshare has a set of rules about how they want it set up. They want every lesson should have an introduction, it should have a description, it should have a class project, and over the months, I've managed to violate every single one of their rules. To the point where they literally deleted what I had up there, much of it. And then I got a letter from somebody who said, Dr. Whitehill, your videos have been deleted. How can I see them? I would even pay for them. Which was, you know, which is what they, you know. So I was thinking, okay, great. So I wrote back to Skillshare, and ultimately I shared with them the third letter, the second letter that he sent to me, and they wrote back to me, and they gave me this. You do this, this, and this. That's it. Those are the rules. I said thank you very much. Goodbye. My 21 videos are up on the web as we speak on YouTube at Laird Whitehill's Astronomy. You can see all of those videos up there. You can see and hear yourselves ask questions. Okay? And I would like to read you my one and only review. And I read this to you because it's just as much about you guys as it is about me. Because without you, this class wouldn't work, right? I can't do this to a screen and talk to a screen and educate a screen. I need you guys, right? You need me, I need you. It's a deal. So this is as much a review of you guys as it is a review of me. This guy is an MD, Dr. I won't read his name. Dear Dr. Whitehill, hi Dr. Whitehill. Even though I went into medicine, I have loved astronomy and physics my whole life. I still watch and read as much science as possible, so I was really happy to come across your videos. I can't tell you how much I enjoy your explanations, everything from the fact that Elon Musk's Hyperloop is really a gravity train, to the plans for the orbiting lunar station, to the successes and failures of our various probe missions. I really like the casual presentations, and I like that you bring in multimedia to your talks. We just don't get this type of information anyplace else.
That's very nice.
We either get too little information, like in 10 to 20 minute TED Talks, Or we get actual course presentations that start with, frankly, boring basics and feel like they have to briefly touch on a huge list of topics to be able to say that they have completed the course curriculum. I subscribe to the great courses, and I have watched nearly all of the science, physics, and astronomy courses. Really? And he likes my stuff? The Higgs boson course was great, but again, everything is devoted to just a single topic. Your lectures are more like we are getting up and up to the minute news feed, what's going on in the world of astronomy, space exploration, science topics, time you spend gathering and curating, and then there's more. And at some point, I ask him a set of questions, and one of the questions is the idea of me having fun, not necessarily the class, but me, is a good way of positioning the lectures? Is that a good idea or not? And he says, yes, you having fun is what makes the course so fun and appealing to others. Okay, well, I'm getting validation for what I'm doing. This is the first, it's okay that you guys like me, but it's terrific that somebody who doesn't know me thinks that what I'm doing is exactly what I'm intending to do and likes it. So, so I am, as far as I'm concerned, one review is all I need. You guys come, that's great, but one review from somebody I don't know, that makes my day.
Your personality is what makes the course.
I don't even know.
When we Google that, do we put in spaces or
No.
Laird,
You go on YouTube.
Oh, on YouTube.
And then you can type all of that. That's not a website, that's a search term. Okay, and so you can leave a space to say, where did I put my water?
Just YouTube.
YouTube, okay.
Yeah, you can just do it without YouTube, it'll come up. Now I gotta find my water. Did anybody see where I've misplaced my water?
Probably on the shelf behind you.
Yeah.
I didn't.
I really did have water, and I really know that I had. These days, when I'm doing this, I get involved in editing. So this class not only takes the time it takes to prepare it, but then I go back and then I have to go edit this stuff because I have to edit out the part which I was just doing where I was looking for the water. So I have to edit that part out. Okay, so this part will not be or will be in the video. Who knows? It depends how funny it is when I look at it. Okay. All right. So, so we started out with 2 weeks ago. We started out. There were not enough people in the class, and I had prepared this lecture on some aspect of the Big Bang, and then there wasn't enough people. There were 12. There's 12 today. And I decided to punish you all by lecturing you about things that you would have to know if there were more people there anyway. So I told you about supernova explosions, and I told you about a few other things. But given the way that this class works, only half of you were actually here for that lecture. The other half will come next week. For some reason, they think it's every other week. So if everybody who came, I'd have like 20 people at least in this class. But it turns out the people just come on alternate Tuesdays. So I started getting involved in this thing called the Hubble Controversy, which is an interesting conversation about something that seems to be wrong with the Big Bang. And I thought that would be a good topic. So as I got deeper and deeper and deeper into it, I got further and further into the Big Bang and further away from the topic that was in fact intended to be like 2 weeks ago. So we probably won't get there today either. Because the Big Bang happens to be a big deal. And the more you learn about it, the more it is. So starting out with this, okay, so that's a picture. So I have to turn this camera towards it so that folks at home can see anything. This turns out to be really poor when you look at it on the web. Okay, this picture you don't see the reds and the blues, and you could hardly see anything at all. So those people who are at home looking at this thing, trying to imagine it, go research the Planck version of the Big Bang. And I should figure a way to put these URLs on the screen. One day I will. But anyway, so this is like the Big Bang. Not the Big Bang. speaking wrongly. This is a picture of the universe as at the moment of conception that we could see it at, which is about 400,000 years after the Big Bang. So we had a Big Bang. Then last week I discussed stuff happened, and then at a certain point stuff stopped happening, and then you get the baby picture of the universe taken at 400,000 years old. Before that, there was no way of taking a picture of the baby picture of the universe, although that might change because the universe now has, the universe, the human race, have a new way of looking past this little place. We have gravitational astronomy. Gravitational astronomy didn't exist 10 years ago. It didn't exist when this project was conceived. Gravitational astronomy might let us see back beyond this wall here. This wall is not a wall, of course, at all. It's just, but it is in some sense. Everywhere you look in the universe, there is stuff that is coming to us from that, from this. It is called the cosmic microwave background radiation, and it comes from us from all directions, there, everywhere, and it's still coming at us from 13, almost 14 billion years ago. That light that's coming through my eyeball right now that I cannot see because it's really not, my eyes are not designed to see that radiation, but if I was born with radio telescopes instead of eyes, then I would be able to see the radiation from the Big Bang, and it would look remarkably uniform everywhere I looked. Everywhere I looked, it would be exactly the same, amazingly boring. But if I was born with not only a radio telescope for eyes, but also the ability to distinguish intensity levels at the level of 1 part in a million, then I would say, oh, over there I can see it's red, and we're going to call red the color that is hotter, and blue the color that is cooler. And we will say, I see splotchy red spots and blue spots, and that means that that I can literally see some definition in the skies in the skies above me. I could literally see definition in the 1 part in a million. Yes.
If you would have lived just 400,000 years after the Big Bang, a little bit later, would it have been in the visual area or not? Would you have actually seen it?
In what area, please?
Would it have been in the area of the Big Bang? Okay, when the Big Bang occurred. Okay, after the Big Bang, 400,000 years later, you get this. Okay, but this picture has it took 14 billion years for the light to get to me with my radio telescope eyes, so that I can take this picture. And so the light that I'm looking at is 14 billion years old. Mm-hmm. Kurt is asking, what happens if I happen to be around 14 billion years ago? Mm-hmm. What kind of eyeballs would I be needing to see the light, right? And I would not be needing radio telescope eyeballs. So the answer to that question is, there is a certain epoch. It is probably around that time, but in fact I actually saw let me see if I can. I saw a list of things, and there is one epoch in which you can definitely see the light as visible light. So the light was incredibly invisible. It was like X-rays, gamma rays, and then the light rays, as the universe expanded, became X-rays, and then it became ultraviolet, and then it became visible light. And at some point, while the universe was getting bigger and bigger, the universe expanded and sucked the life out of the light rays. And I say that with all generosity towards general relativity. you can suck the life out of a light ray. All you have to do is you take the space that it's in, okay, and you expand it. And while the speed of light cannot be altered, it's constant. That's the rule. You can take the space that the light ray is in, and you can move it faster than the speed of light, and expand it so that the poor ray of light gets stretched. Now, this is actually, I've never read it quite like that, but that's true. I think that is true. It's just the worst way you could possibly explain it, but it's true. Light gets stretched as the universe expands, and as it gets stretched, the wavelength gets longer, and therefore it's no longer the wavelength that we need to see, which is really, really small wavelengths, smaller than a hair, much smaller than a hair, goes through our eyeballs, and we can see that wavelength because that wavelength excites the rods and cones of our eyes, and we can respond to that wavelength. Our bodies are designed to respond when that ray of light hits us in the eye. We see that wavelength. Our bodies are not designed to see wavelengths that are this long, okay, and nothing in our eyeball can respond to that, but radio telescopes can respond to those wavelengths, and they where was I going with this? So the wavelength goes past visible into infrared, and then ultimately to radio waves. And there's actually dates. And there's a date. There's actually a date. This is crazy. Let's see if I can find it. There's a date where the universe is. There's a timeline of the universe. Let me see if I can find it. Timeline of the universe, and in that timeline, there's a date where where water can exist in liquid form. There's literally, the universe there's light everywhere, okay, and the temperature is a balmy temperature. The universe is at a balmy temperature, and the balmy temperature is everywhere because the light is before the stars have formed. Stars haven't formed yet, but the universe is at a balmy temperature, and if there were planets at that time, the planets would be subjected to this balmy temperature, and the liquid water could exist on these planets, and on those planets life could have originated if life was prone to originate very quickly. We don't know how quickly life originates. You could build a planet and life could happen like that. We don't know how quickly life originates. It's one of the big mysteries of our time. We don't know whether life is called for or is in fact unusual. Let me see if I can find that timeline. I guess not. It's not on this list. This is where I'm going to be spending a lot of time lecturing from this screen, so that's okay. I spent the time getting it. So anyway, back to this. So when they got this picture of the universe, where reds are hot in the 6 decimal places and blue are cold in the 6th decimal place, they realized that all the other decimal places were the same. The universe is at 2.7 degrees above absolute zero. 2.7 degrees above there's an absolute zero. Nothing can get colder than. There's no absolute temperature. Things can get crazy hot as much as there's no top to temperature, but there's a bottom to temperature, and the bottom temperature is zero. Okay, but not 0 degrees centigrade. That's minus 273 degrees centigrade. So there's another scale called Kelvin. Kelvin. And Kelvin starts at 0. So that by the time you get to room temperature, you're around 300 degrees Kelvin. Okay, so we're about 300 degrees Kelvin. Absolute zero is 0 degrees Kelvin. The universe is at 2.7 degrees Kelvin, and that's the body that is radiating, a 2.7 degree black body, which if you were here and looking out among you, very few of you were here when I was punishing the class with an explanation of black body radiation. Who was here for that? Who who was here for my explanation of black body explanation? Right. No, and so then there are some people who are here and don't remember. That would include me. Because, see, in these lectures, by the way, I have to tell you, these lectures, I have to prepare these lectures literally the night before or 2 days before. Because if I prepare them a week before, I don't remember what I read. Right, so I have to literally reread the stuff every time. And that's why the lectures keep moving from where I intended, because I never read the same thing twice. So I read that thing 2 weeks ago, and then I don't remember it, but I'm reading something new now, and that becomes the new lecture. So that's why the lectures seem to drift. Anyway, so the sky is at 2.7 degrees everywhere. Now that's a problem. It's not nice. It's very not nice, because how did that part of the sky get to be 2.7 degrees Kelvin, and that part of the sky get to be 2.7 degrees Kelvin, since they've never met? You see, that's so far away and that's so far away that there was no time for these two to ever been close together enough to exchanged handshakes. And handshakes is what you do. You take this room is filled with gas. No matter where I go in this room, the temperature is the same. That's not a coincidence. It's because this room has had the chance to exchange heat with the radiator over there everywhere, so that everywhere the molecules in this room have all had a chance to introduce themselves to each other and become the same temperature, as they've agreed on that. If there was part of the room that was cold and part of the room that was warm, in very short order, that would change. It's called entropy, and things just get messed up until they're the same. That's entropy. That's the worst explanation you'll ever hear of entropy. And so, but they need to be together and to reach the same temperature. Yes.
Not equilibrium, entropy. In
Entropy.
other words, it's a mess.
Right.
I mean, entropy to me, in a very, very amateur way, means a kind of a mess.
Yeah.
Whereas equilibrium, it's
Oh,
the old-fashioned chemistry.
Okay. You're absolutely right in some way. It is an equilibrium because
Okay.
before when you have hot and cold, they're not in equilibrium. When they come together and they're the same temperature, that's equilibrium. True, but think of it this way: you use the word mess. Okay.
Yeah.
Okay. So there's hot, there's cold. That's not a mess, because you can go over there if you happen to be a hot person. You can come over here if it's a cold person.
Okay.
When they two come together and they mess up with each other, then they have reached the sameness, and that's the mess.
It's a
Okay?
mix.
It's the mix. It's the mess has been mixed together. So entropy is the mixing of all things so they become the same.
Entropy is a tough
I
word.
thought
Okay,
entropy is
mixing.
when everything falls
Okay.
apart.
Entropy is not when everything falls apart. Entropy is when everything becomes, everything falls apart in the sense of that if you take an egg, okay,
Yeah.
which is very nice, okay, and then you let it, you drop it, and it becomes little pieces. It falls apart. There's no way that egg is ever going to come back together. Because entropy goes in one direction towards more disorder. So that's why you have the opinion that it falls apart. Barbara, would you tell them to be quiet? Barbara?
Close the door. I tell them every week.
You know, those people just walked in to talk.
They shouldn't be. Downstairs.
So entropy is not, you can see it as falling apart. The universe falls apart in the sense of the things that were good become bad and everything becomes, but it's more uniform rather than, it's like the temperatures become the same. The stars die out. So the stars became the same temperature as the planets and everything gets cold. You know, so that's like falling apart. But it's not, that's not the right explanation for it. I'm just dismissing entropy in 2 seconds to get to what I'm talking about, right?
Okay.
But you can keep asking questions about it because that diverts the class from the topic, you know, which is of course the best part. So there's no way that the universe could have the same temperature here and here, and that was So you have the Big Bang Theory, which has existed for over 100 years, and you have a little problem that you can't explain it, because you can't explain why it's so uniform. And when they looked at it more carefully, they saw it's really uniform, and they said, yeah, this doesn't work. Why is that? So about 10 years ago, maybe more, a guy named Alan Guth, D-U-T-H, he said, I have an idea. Let me concoct an incredibly insane idea and see if I can sell it to the rest of the scientific community, and let's see if it flies. Well, of course, it was not his reasoning. But it is true that he has come up with the craziest idea that anyone has ever come up with, I think, in the annals of science. And it has become almost dogma. The idea is that the universe, while it was busy Big Banging, did an extraordinary thing and went super Big Bang. During the Big Bang, there was a bigger bang. And the bigger bang took the little universe, the itty bitty baby universe that was so very small, okay? Let's say the size of a DNA molecule. And but it was smaller than that, okay? It was much smaller than the size of a DNA molecule. We're talking much smaller. And that little thing, DNA molecule, size, we're talking relative size here, became like 10 million light years in a trillionth of a second. So space expanded faster than the speed of light. In a trillionth of a second, something incredibly small became incredibly big in an incredibly short amount of time. That's what he wants you to believe. And while you may not believe it, because that may sound incredibly silly, the rest of cosmologists tend to believe it, because it solves so many of the problems that they were having. One of the problems that they were having, I didn't prepare this part of the lecture, but I have to look for this. This is Maxwell's equations. It is among the most beautiful set of equations ever invented until general relativity came along and quantum mechanics came along, and those are pretty damn beautiful equations. But this is the kind of equation where when I was in college, I don't wear T-shirts that ever say anything on them. You never see anything on them. But I would wear a T-shirt that had this printed on it, and I would even have it tattooed on my body. I met a woman once who had Schrodinger's equations tattooed on her body, and that was an impressive feat. But that's another story. Yes, Burning Man. But these equations are the four equations that describe electromagnetism. Electromagnetism is the story of electricity and magnetism and how they are one and the same. That electricity becomes magnetism, magnetism becomes electricity, and they're parallel in all regards. And these equations are, they don't unfortunately look enough like each other, but look at these equations. You have this one, del cross E is equal to some derivative of B. And del cross B is some derivative of E. Like that. Yeah. So these two are very parallel, okay? And these two, del dot E is something, and del dot B is nothing. It would be very nice. So this says that if you look at an atom, an electron or a proton, you see something, because there's something there. This one says you look at a magnet and there's nothing there because there's a north and a south. So the problem with the north and a south is they add up to zero more or less the further you get away from them. An electron or a proton, no matter how far you get away from it, it's still there. There's a proton, there's a proton, there's still a proton. Protons exist by themselves. North and south does not. There's no such thing as a magnetic monopole. It doesn't exist in nature. But this equation says, please, Give me one. I could stick it right there. It belongs right there in the equation. Magnetic monopoles. Why don't we have magnetic monopoles? Why didn't nature invent them? They belong in this equation. This is beautiful. Make it more beautiful. The fact that it doesn't exist is disturbing to people. Okay? Not just because of this, but because of other reasons. So you need to come up with a reason why a particle that doesn't exist. Okay? You need to come up with that reason. Well, the guy who invented inflation started out with asking the question, well, how can I explain the non-existence of this this imaginary particle? And he was able, through his mathematics, to explain why the universe has no magnetic monopoles. There's no thought that I'm going to be able to explain that to you. And the reason for that is I don't understand it myself. But I do know that that's what started him going. And as soon as he got there, he said, oh, right, inflation, that would do it. Inflation would make the magnetic monopoles not happen at all. There wouldn't be any in the universe if I could invent a universe that expanded so quickly that magnetic monopoles could not exist. So he invented inflation, and then inflation explained everything else.
This is Guth now.
This is Guth.
That did
Alan Guth.
the fast expansion of the universe,
Right.
this thing, and like,
Yes.
okay.
Right.
I heard him at the fair.
Oh, you heard him at the science fair?
Yeah, several years.
And was he fun? Was he interesting? Did you understand what he said?
Well, he was with the others.
That's such a good
They were-
line. He was with the others.
I mean, there were like four of them. Brian Green, he was there.
Oh, Brian Green, right. So did you understand what Brian Green had to say?
At the time, I did.
Okay.
Don't ask me. Right?
No, don't even ask me. I've read his books and I don't understand. At least I haven't. Actually, they are understandable. They are. It's Lisa Randall
Oh,
who,
she's great.
I heard her too.
yes, so Lisa Randall, I heard her.
I don't
her.
understand.
Well, I saw her and I really liked her lecture, okay? And then I read her book and I didn't understand anything starting at page 1. And it was designed for people like me. You know, so she's
Is
really...
this the first book? Because even I understood the first part of it. She kind of introduced me to a part of physics.
Yeah.
This must be the second book?
Yeah, probably.
Whatever.
I
Whatever.
heard her
she's very
lecture
good.
at the museum.
No, I may be underestimating,
I can
I may be putting my own capability down. I do have the ability to understand this.
No, I know.
I just have
I'm
to,
just
I just can't be
amazed that I
skimming through it.
Didn't understand.
Maybe page 10. Okay.
Okay.
All right. Okay.
So, chronology of the universe, okay?
So that means the Big Bang did not happen the way.
No, the Big Bang is dogma. The Big Bang is dogma.
But you said there was a problem with it.
Oh, the problem with the Big Bang, the lecture that I was going to give, that still haven't given and will still not give today, said there's this little problem. And it's a little problem. All it means is that there's some new physics. We get excited about new physics. There's something that we can't explain that we need to explain, so we're going to have to explain it. But that doesn't mean the Big Bang is a problem. It just means that there's something we need, it's something that this information, the problem will tell us, somebody will come up with the answer to explaining the problem, and then we'll have new physics. That's exciting. So I'm not going to go down the route of what the problem is, because that's the lecture that I'm skipping. Okay. Because we're going to the Big Bang. And the Big Bang is, there was a time before time, there was a time when t equals 0, okay? Now, if you multiply 0 by 10, what do you get? You get 0, right? So 10 times, so 10 times later than 0 is still 0. So nobody does that, okay? What you do is you count backwards from now and divide by tens. Okay, so now is 14 billion years from the Big Bang. Divide by 10 and you're now at 1.4 billion. Keep dividing by 10 and you keep getting closer and closer to the Big Bang, right? You get to 1 million years and 100,000 years and then 10,000. You get there. You keep dividing. You can keep dividing. because all you're doing is you're playing with mathematics. There's no reason that I can't write a number that's smaller than any number you can think of. Let's think of a number that you cannot, the smallest number you can think of that is bigger than 0. Let's say that you say that number is 10 to the minus 42. Okay? Let's say that is the smallest number you can think of. Well, I can think of one smaller. It's 10 to the minus 43.
Right.
Okay?
Right.
You see? So there's no number that you can think of that I can't think of a smaller one at. There is a point at which you want to stop. Okay. 10 to the minus 3, 10 to the minus 43 seconds after the Big Bang is the beginning of the conversation. Before that time, we physicists, and I'm including myself in this category for the purposes of this discussion, we physicists cannot say anything. We throw up our hands and say, I don't know what was going on before that time. Really? Really? You're saying that after 10 to the minus 43 seconds, you have a clue? Okay? So you have a story you can tell starting at 10 to the minus 43 seconds, but before that you have nothing? Yeah, you have nothing. Why do you have nothing? Please explain that to me. The reason you have nothing is because there's a thing called quantum mechanics. And quantum mechanics has this quantum mechanics is one of the laws of nature that has been not disproved one whit since the day that it was discovered or invented, depending on how you look at these things. Essentially, quantum mechanics says there is a limit to how much you can ever know. There's a point at which things become not just unknown, but unknowable, in the sense that and I always, in this class, I always use the word, before then, there could be clowns. Clowns could be doing, the universe could be explained entirely by the action of clowns, and that's as reasonable an explanation as anything else, because, in fact, while clowns is unlikely, so is everything else. Anything you think of is fine, because nothing we think of is provable, so you're free to invent anything you want, including clowns. The proper word for that, however, is the Planck Epoch.
Wow.
You know, point the camera at this for a second so you can see it. Yeah. The proper word for that is Planck Epoch, and it was written on the screen there. It says Planck Epoch there. So, in the Planck Epoch, before 10 to the minus 43 seconds, there was clowns, or anything. It says, I'll read you the description, rather than giving you my explanation. The Planck scale is the physical scale beyond which current physical theories may not apply and cannot be used to calculate what happened. During the Planck epoch, cosmology and physics are assumed to have been dominated by the quantum effects of gravity. Now that's interesting. Gravity is this thing that Einstein invented that explains the motions of everything in the universe, and gravity is the very weakest force in the universe. Very, very weak. Very weak. And well, so weak that the electromagnetic forces of the atoms in the floor tiles below me is capable of holding me up, and gravity can't pull me down. So electromagnetic forces are strong. Gravity is weak. Got a whole planet pulling me down. Got a floor tile holding me up. A floor tile wins. So the gravity is only really real and at large scales. And if you compress gravity into smaller things, it becomes something that becomes like the small things that invade our universe, called atoms. And when you get them when you get gravity as small as an atom, which is not explaining it right, it begins to have effects at the scale of an atom. And if you compress it to something that is incredibly small, like the beginning of the universe, gravity begins to behave like quantum things, like atoms behave like quantum things. So there can be something called quantum gravity. And while we never invented quantum gravity, because we can't do an experiment to test for it or even do anything with it, we imagined that that was the era in which quantum gravity existed, along with the other quantum things that went on during that time. There was a time when there are 4 forces in the universe. Yes?
I don't quite understand that you said gravity is a weak force.
Yes, it's the weakest force. It's,
Because
yeah, you can dismiss it
we
entirely.
always thought
Jump out of
that-
planes, nothing happens. Yes.
We always thought that gravity is the kind of thing that put things together to make it bigger, like a planet.
Yeah, so the thing about gravity...
Would you consider that weak?
Yeah, see, gravity is weak. You think gravity is strong. And the reason you think gravity is weak is strong is because if you took 6 pounds of protons, okay, 6 pounds of protons, and you said, I'm going to make something out of 6 pounds of protons, well, you'd have a very hard time putting 6 pounds of protons together because they happen to like to do this. You can't stick them together, okay? The only way you can stick them together is if you put an equal number of electrons. Then you get 6 pounds of schmutz. You get dirt, 6 pounds of dirt, okay? With 6 pounds of protons and 6 pounds of electrons, you get dirt. And there's no electromagnetic force coming out of that thing. So that when you pile dirt upon dirt upon dirt, you can get a planet. But you can't pile proton upon proton upon proton because if you add 2 protons together, they become helium. And they want to have electrons running around them. So pretty soon you got a neutral helium atom. You can't make a pile of protons. And that's why you never have the sense, that's why gravity is so weak, that's why it's so weak. That's why you perceive it as being so strong, because it's the only thing that accumulates. More and more of it make more and more of the force. But you can't make more and more of the force of protons. So although they're much stronger, they never compete in your world. Occasionally, you see, you rub your comb and then your hair stands on end, and you see that there is some sort of electrostatic force that's pretty amazing that can get your hair standing on end against the force of gravity. But that's about the only time you ever get to see the strength of the electromagnetic force. So gravity's weak, but you can combine a lot and that you get a very strong thing. So the strongest forces in the universe are gravity because of the amount of stuff you can accumulate to put it together. So black holes, giant forces, amazing forces, but nevertheless, you have to put an amazing amount of stuff into a black hole to get it to be that strong. Whereas you only need a few pounds of protons to do the same thing. Yes?
Just in reference to what you were talking about before, Cantor invented or visualized
Cantor.
A system of mathematics called transfinite mathematics.
Right.
In which 1, 2, 3, there's always a higher number.
Yes.
Doesn't exist. There's a cardinal number. The arithmetic properties of which are radically different than usual. In other words, the first number is called Aleph No.
Yes.
And for instance, the arithmetic property is Aleph No times 1,000 equals Aleph No.
Yeah.
Aleph No times 1,000,000,000
Yes.
equals Aleph No.
Yes.
So has this system ever been applied to...
Has a system of multiple infinities ever been applied to this business we're talking about?
Yeah.
So this, the idea of multiple infinities is not something that dismays physicists. For example, if you take a line, okay, and you divide that line into halves and quarters and eighths and sixteenths and like that. You can do that an infinite number of times, okay? You can take any of those divisions, between any of those divisions, and you can put an infinite number of points between any one of those divisions. So there's no reason why you can't have, in normal everyday parlance, infinities that are bigger than other infinities. And that's all he's talking about, infinities bigger than other infinities. That's just a mathematical truth. It happens in mathematics, it happens in physics. It's not something that needs to be discussed. It's just something you know. Multiple infinities, isn't it cool? Yes, it's cool. How does it apply here? I don't think it does. Okay? All right. So the thing is, there are four forces in nature. Four and only four. Is there a fifth force in nature? That would be cool. Nobody has raised their hand and said, I have proof that there is one. There are plenty of people who have raised their hand and say, I have an idea, maybe we could go looking for it here or there, but there's no proof. Four forces. Gravity is the weakest. The next one is called the weak force.
Right.
Okay? No, the next one, the next one is
Strong
called,
force?
what?
Strong, no.
Yeah, there's strong force, and then there's electromagnetic force. I think the electromagnetic force is I think it's gravity, then it's electromagnetism, then it's the weak force, and then it's the strong force.
Fission and fusion.
The forces. And I will at some point, maybe today, maybe not, explain what those are. But the point is that they are separate and distinct from one another. Two of them, electromagnetism and the weak force, have been shown to be the same when you get really small. If you get really small and really tight, those two are the same. We think that if you get really smaller and really tighter, then they would also join forces with the strong force and they would all be the same. See, when they're all together, and then the universe expands, then they go their separate ways. I get to be weak, I get to be strong, I get to be electromagnetic. Those forces early in the universe were thought to be combined, as well as gravity. Gravity, we want to throw the idea of this is called the grand unification of all forces. The grand unification of all forces took place in our imagination at the very beginning. After the Big Bang began, there was after the Planck Epoch. In the first time that we began to talk about things as if we knew anything at all, the four forces were combined as one. This, of course, is theory. It is not dogma. It is a fond wish. And the reason it's a fond wish is we have built machines that are designed to tell you what the physics were when energies were big and the universe was young. And we've built these machines to tell us the answers to that question. These machines cannot answer this question. They're not built to do that. Yes?
If these four forces were very, very small.
If these forces were very, very small.
Infinitely small,
Compacted.
or inconceivable, whatever.
Yeah.
Wouldn't it have taken something that we haven't named yet, a fifth force, to cause the Big Bang?
It would, if these were four forces, wouldn't there be a fifth force to cause the Big Bang?
Yes.
There's a thing, okay? It's a force. It's called the inflaton, okay? The inflaton is an imaginary particle or force that existed in this story that I'm telling, which hasn't occurred yet. In this story that I'm telling, the inflaton is down here in this list of things. And it becomes the force that blows up the universe. But it happens after the Big Bang, because the Big Bang happened at t equals 0, or t to the minus 43, 44, 45, 46. There is no postulated force, fifth force, that created the Big Bang.
So was
There
it
is
created-
no postulated reason. Okay, I mean, there are plenty of postulated reasons, but they do not include a fifth force. Okay, the word fifth force is reserved for those wet dreams that people have for other reasons. The reason for the Big Bang is people don't throw the word fifth force at the Big Bang in order to explain it. Okay, they have other things they're talking about.
I just want to ask, is gravity measured by instrumentation?
Is it gravity measured by instrumentation? Yes, yes. How much do you weigh?
About 190.
Yeah, that's your instrument is what?
My what?
The instrument you use to measure that is what?
A scale.
Yeah, there you go.
Okay.
Yeah, there are ways to measure.
That's one way.
Well, no. You see, in order to measure the force of gravity, you need to measure the force of gravity, and you need to know you can measure the force of gravity. You need to know the mass of the Earth, but how do you know the mass of the Earth? It's hard to know the mass. So there are ways to measure the force of gravity. One of the things that you do is you take two globes in your freshman science class, okay, and you put these globes next to one another, okay, and you see whether they can influence one another, and you actually see whether they can pull on one another, and you have these very sensitive scales that are designed to measure these two objects as they pull on one another, and you can actually measure the force of gravity. It's done,
Solid globe?
solid globes, and they put them near each other, and you measure the force between them. It's a very sophisticated experiment, and not the way you imagine with two things pulling. It's more complicated than that, but nevertheless they can measure the force. So yeah, force of gravity is measured. Force of all these things is measured. Okay, so 10 to the minus 36 seconds. Okay, from 10 to the minus 43. From 10 to the minus 43 to 10 to the minus 36. Look how many. That's six. That's wait, I can't do the math. That's 7 divisions of time, right? I mean, if you think of these things in terms of there's only 43 divisions, maybe 50. You take 10 to the 43, you multiply it by 10 to the 50, or I don't know, do the math, 10 to the 52, and you get where we are now. It's just 52 slices of time. So if you think of each slice is a reasonable time to be discussing things, then each slice has like a lifetime. People enjoyed, went to house parties. Any living thing that happened to be existing at this time, in this time frame, could have enjoyed a full lifetime worth of stuff going on between 10 to the minus 36 and 10 to the minus 37. I mean, these are epochs where the universe was doing stuff. The fact that it's incredibly small doesn't mean that stuff wasn't happening, that the stuff that makes us all what we are today wasn't being cooked in those times, even though they're incredibly short periods of time. So, grand unification epoch, the temperature is 10 to the 29th Kelvin. This is 2 Kelvin. That's 2, it's essentially 1 with a 0 next to it. This is 1 with 27 zeros next to it. That's the temperature here. The temperature here was 10 to the 32 Kelvin. Very hot. Very hot. The Big Bang was very hot. Very dense. Then comes the next epoch. This is the inflationary epoch. This is the time, this is the one that makes it all crazy. Okay, this is the one that is hardest to believe of all. It says here, cosmic inflation expands space by a factor of the order of 10 to the 26th over time order of 10 to the minus 33 seconds. 10 to the 26th expansion in 10 to the minus 33 seconds.
That's goof, isn't it?
That's goof.
Okay.
That I mean, what we could try to do here for the rest of the time is to try to explain how big that is. But that's insane on any level. 10 to the minus 33 seconds, the universe expands by over 10 to the 26.
Sorry.
That's like the human hair, the DNA molecule expanding to 10 light years in that period of time.
Not if it's a balloon.
It's a very big balloon. And so, why did he invent inflation? He invented inflation so that while the universe is together right here. Earlier, it's all together, and it's talking to another. And everybody says, what temperature should we be at? And they all agree that they should all be at 10 to the 29th degree Kelvin. And the universe is so small that they can all have a conversation between each other and reach the same temperature because it's so close together that they can communicate, because the speed of light is able to travel between those points, very small points, and everybody can agree using their communication devices that they should reach the same temperature. And then inflation takes over and says, and now that you guys have agreed, we'll just spread you out, but you'll all be at the same temperature forever. And because if you didn't have inflation and these things got to expand slowly, they wouldn't have the same temperature. These guys would go south, these guys would go north. They would be different, much different, and the universe would be non-uniform, making noise.
Sorry.
Universe would be non-uniform, and one of the rules of the universe has a few rules.
So
And
there must be a God.
There must be a God, yeah, right? At least, maybe two. Why stop at one? What was I saying? I did lose my train of thought when you said that. I completely lost my train of thought. Okay.
They were close enough to talk and then they weren't.
They were close enough to talk and they weren't. That's right.
Close enough to what?
Yeah, we have a question.
Well, talking is being fun.
There would be considered in the universe, in the solar system, there is uniformity, because the sun stays where it is, and the remaining planets from our own sun stay where they are, pretty much.
Okay, so you're saying uniformity. So the problem with you're talking, you're using uniformity, and you're using the sun and the planets. Okay, and I know where I was going to go. I know where it's going to go, and we're talking about uniformity. So you got that right. But what you got wrong was the scale. There is a thing called the Cosmological Principle. And as I said, it's like a law. It's really not a law. It's a fond hope. Okay? The fond hope is that the universe should be the same everywhere you look. When I say you got it wrong, the part you got wrong was you missed on the idea of the universe. The solar system is such a pipsqueak part of the universe that it shouldn't be counted as part of the universe, given that I'm talking about the universe. Okay, so the fact that the solar system is or isn't anything you said has absolutely no relevance to the universe, which I'm trying to give you some sense in this class of how big the universe is. That's one of my jobs. Tell you how big the universe is, because it's really big. And it says, my sign outside says it's really big, and it's even bigger than that. And so in this class, in the next few classes, I'm going to try to give you a sense of what even bigger than that
So how could
means.
there be more than
What?
How could there be more than one?
How could there be more than one universe? That's where Howard's question comes in. Infinity of infinities. You see, if we go on to infinity, and he talks about what he was talking about, how there's Aleph 1, at Aleph 1 times 10 is still Aleph 1. Okay, that means that if you multiply infinity by a number, you still get infinity. Okay, but then what about the fact that beyond infinity there's another infinity? Okay, so there's an infinity of infinities. So this infinity there's a bigger infinity, and then there's a bigger infinity. So
That's God.
that's where we go multiple universes. That's where we go with that. We go infinities and infinities. That's how we get there. With all of null, all of one, all of two, we get there. But when we're talking about this universe, which isn't on the screen anymore, when we talk about that universe, this one, it should be uniform. I said the universe should be uniform. Pay attention. It seems as if the universe isn't quite uniform. It's supposed to be the same everywhere you look. That's the rule that we set. The universe should be the same everywhere that we look. Otherwise, we better get an explanation out of this. And it doesn't look, this particular spot in particular, it looks rather strange. It looks like a cold spot.
Yeah.
It does look like a cold spot. People are talking about this like it means something. Okay? So stay tuned for what somebody's next best idea is for that. And believe me, multiple universes gets touched on when they talk about, oh, that's where one of the multiple universes is touching us. Okay? So just in case, Yes.
I still go back to what I thought last week, which is that we think and we have this fond hope that everywhere it's all the same.
Right.
But we're projecting our own experience, our own mind on the whole thing.
No projection. We actually have measurements. These are measurements. These are not the only ones.
For us to talk about other infinities, we can only wrap our head around a certain amount because we're limited. It seems to me we can only wrap our heads around just so much, so that if we say that the principles that guide the universe are certain principles that will be there everywhere, I don't really see why that should be so.
Well, the idea that it's a postulate, really. Okay, it's a postulate. Okay, and the postulate is that the universe is the same everywhere. Okay, and then we go and test. So, for example, somebody's postulated the universe is the same everywhere at this scale, and that turns out to be wrong. The scale of the solar system, clearly wrong. The scale of the Milky Way, not right. At the scale of multiple Milky Ways, not right. At the scale of multiple clusters of Milky Ways, not right. They keep adding to the size that they call the size where this chunk of universe is the same as that chunk of universe, and they keep making the chunks bigger. Okay, and every time they have a bit better measurement, they say, "Oh, still not uniform enough. I need to make my chunk bigger so that the universe then at this size is now uniform, and this is the same. It's got the same distribution of matter, not exactly the same exact matter, but the same distribution. In other words, so much of this size, so much of this size, so much of this size. Distribution of matter is the same everywhere in this chunk as that chunk. I can now say the universe is uniform. They really say, the way they say it, the universe seems to be uniform at a scale of, and then they say, we think the universe is uniform at that scale, but maybe it's going to be a bigger scale that we need to take before we can say the universe is uniform at that scale. They haven't finished expanding their arms for this. They've just hoping because this is as far as they can see, they say, well, this is as far as we can see. I think it's good enough here. But if they could see a little further, they would probably say, well, it's probably better over there. Yes.
Yeah, Doctor, what's causing Andromeda to collide with the Milky Way? What forces or what's the history?
The Andromeda is colliding with the Milky Way. This is what's called, there's a word in astronomy, it doesn't seem like the right word, but it is. It's called proper motion. It doesn't mean that it's proper. It means that it's more or less it's improper. It means that, see, the universe is expanding, so everything's moving away from everything else. Everything that doesn't conform to that rule, you would call it improper, even though the right word is proper. So the universe is expanding, okay, locally, the universe can do anything it wants. Because the piece of the universe that is expanding, you need to take this volume and say, well, it's expanding to this volume. But the part you're talking about, the Andromeda and the Milky Way, this. And these guys can be doing anything they want, given that the whole thing we're talking about is this big. This is the universe expanding. And this is, by the way, I'm not holding the universe in my hand right now. I'm only holding the local universe in my hand. The really local universe, of which Andromeda and the Milky Way happens to be a teeny little bitty part of it. Okay? There's the local, then there's, I haven't shown you pictures of the universe, and I'm not going to do that now, because I can't pull it up. But the universe is, because that's what I want to show you. The universe is bigger than you think. That's the point of this lecture on some level. The universe is bigger than you think. So Andromeda is heading this way because basically the expansion of the universe hasn't had any effect on what way Andromeda is going and the Milky Way is going. Has virtually no impact. Because the space that we're talking about is much bigger, and Andromeda is in a small part of that space, and things can go any way they want. If you take a balloon, and you look at it, I don't think I can do a balloon analogy here. So anyway, so that's it. The class, class thingy, and attendance. Okay.
And you won't be here next week.
So I will not be here. I will not be here
Next week.
No, not just next week.
No, but you're not here. It starts when you're not here. It starts next week.
Yeah. So next week, I bought the Cosmos series via Neil deGrasse Tyson on Blu-ray, and I brought my Blu-ray player, and they will be playing it while I'm away. So for those people who really just don't come to see me, they just come because there's an empty chair, those people will still have something to do when they come next week. There will be Neil deGrasse Tyson doing the Cosmos series. And I will be away, I guess, for about 4 weeks.
You come back on that day?
No, I know. I'm not here then, and I'm not there then. Okay?
What time will the substitute film be shown?
Same time.
20 hours. Okay.
Yeah, 20 hours. Although, frankly, the class begins at 25 of, and the reason it does is so I can go to a class that begins 25 minutes later, and the people who come generally think, well, it's optional, and they show up between that time and later, so that if I need to go to the thing that goes on in the Museum of Natural History, I have to start speaking when half the class is here. So I encourage you to come on time, not 5 minutes late, because the reason that it's at such an awkward time is because so I can get out of here on time. And I would also leave early on those dates. I would leave a few minutes early. So class, you'd come and you'd see only half the class if you came at your usual times.
So what time should we come? 12:30?
12:35. The class begins at 12:35. It's on the attendance sheet that you see and pass around, right? It's just that, I usually wait. If I don't have anything happening on the other end, I wait till there's more people. And I vamp till ready, as Woody Guthrie would say. So take a look at my astronomy thing. If you've come often, your questions are there. And you can see how well you like being my willing helpers in these things. Yes?
Wasn't there some discrepancy in the numbers that made the expansion
Yes.
a problem?
That's the topic that I haven't gotten to. That's the topic. And what happened is, as I got further and further into it, I realized that it was less and less important. And the only reason that I was going to bring it up was because it's a mystery. So I said, here's a mystery, I can talk about the mystery, let's do that. And then it turned out that the Big Bang was more interesting. So I'm getting there, and I'll get there eventually. Yes?
Earlier you mentioned in passing the mass of the Earth, and we seem to say the mass of something else that we see from the Earth is a certain size. So what is the mass of the Earth?
What do you mean, there's a number?
Yeah, is there a number?
Oh, sure. Sure, we have it to about 6 decimal places. The mass of the Earth. You can Google it. Mass of the Earth.
Doesn't matter, he's gonna do it.
There it is. 5.972 times 10 to the 24 kilograms. Okay? The fact that it's in kilograms should not upset you, because the number isn't comprehensible to you in the first place. So the fact that it's measured in kilograms, and if you need to know the exact number, multiply that by 2.2. Okay? So it's a large number. The main point of it, it's something followed by 24 zeros.
Is it changeable?
Is it changeable? It changes all the time, because the Earth keeps getting bombarded by things from outer space. So there's tons of stuff hitting the Earth all the time, and so the Earth is getting heavier all the time. But the question is, in which decimal place is that affecting? Okay, and I have a feeling it's affecting it in the 9th or 10th decimal place. But the Earth is getting heavier in the 9th or 10th decimal place. Yes.
One question, how can we be looking for a theory of everything when we're only aware of 4% of everything?
Oh, yes. And of course, this lecture was going to be about that, but I didn't get to that. So it was going to be about that, right? So while this is going to be the subject of this lecture, we didn't even get there this time. Yes.
How hard is it to get a grant to do an astronomy project, and who gives grants?
The United States government gives grants. In order to get a grant from the United States government, you need a PhD in astrophysics. You need to be working for a reputable institution. You have to have a reputation. You have to have a good idea. You have to have other people who think your idea is a good idea. So you have peer-reviewed good idea, and then you have to spend months and months and months writing it. You take courses so that you learn how to write grant proposals, and then you need to know somebody to get it through the grant process, and then you have a very little chance of getting one. That's how you do it. Okay, I know this because my son's wife, that would make her my daughter-in-law, is doing just that and having a hard time. Yes.
In what subject?
If you'd like to write down, if you write down.
Health.
In health, some aspects of health.
Yes. Yes. Yes.
Yeah, Doctor, I want to ask a crazy question. If the atmospheric pressure at sea level is about like 32 pounds per square inch.
14.7. 14 pounds.
Oh, 14 pounds per square inch?
Yeah.
Oh, would it be more healthier to live at a higher level, or even lower than the
Would it be healthier?
healthier?
The higher you go, the bigger your lungs end up being. The people in the Andes Mountains, but I don't think they live longer. I don't think they live any longer. I don't think they live longer. Is it healthy?
Sea level would be the normal range.
Yeah.
Yeah.
I don't know that healthy is better upstairs.
Right.
Yeah. Right. Okay.
14 pounds per square inch?
If we're kind of finished, I just wanted to
Oh, yeah, we've been finished for a while.
remember the
People are
Lisa
just hanging
Randall
around.
book. I read her first one, and she was just going over basic physics that she went over in her freshman class, which is why I got some of it. But the first book was on dimensions, and on the very, very, very small. And why I liked her was she was able to describe to me, like, up fifth dimensions and sixth, and that was that book. And I'm not seeing, except that we don't know what. Well, you said.
You want to see 10 dimensions? I can show you 10 dimensions. You want to see 10 dimensions?
I
I'll
do.
show you 10 dimensions.
And
Here's-
at the
here we
very,
go.
and she said at the very, very, very smallest,
Yeah.
we
I know.
really look at
I know.
gravity,
I
which is
know.
very
I
weak.
know, I know.
So that's what I remember of her book,
This-
like 10
I am being
years ago.
facetious here, but I am not being facetious, okay?
Right, right.
Because I'm
She's
a
very good.
mathematician as well as a physicist. Okay, so
That's all I remember.
y
That was good.
equals f of x. Have you ever seen this? Anybody seen this?
Yeah.
Okay, this
I think
means
so.
that the thing y is a function of x. Okay.
Yeah, I
Guess
never
what that is?
understood it, but I've seen it.
Okay.
Really?
Okay. What it means is for example, there's a
Right, got it.
there's a
Okay.
line.
Right.
This is x. This is y.
Okay, got it.
Okay,
Yeah.
and this is f of x.
Point, right, Okay, gotcha.
And that's f of x. And so this is a one-dimensional plot,
Yes.
okay,
Yes.
of a function, okay,
Okay,
which has one dimension,
right.
okay? What happens if it was f of x and y?
Okay.
Okay, now
Flatline.
we have x and y, x and I'll make it z. Okay, so this is
Okay.
z here now, z,
Okay.
and this is y. And now anywhere in this xy plane is a dot, okay? And then from there we erect the point to this, and that is f of x, y. So this, in this point in space, okay? This point in space, which is the xy space, there is a value of something, some function in that space that is some number 3. Okay?
Okay.
So at this point in space, at this point of y of 6 and x of 12, there's a value of 3. That is the function that the function of x and y gives you. The z value is 3. Okay? That's a two-dimensional function. Okay? Two-dimensional function. Okay? F of x, y, z. Now, it's the room. Okay? And what is the function? The function in this room is the temperature everywhere in this room. The temperature everywhere in this room is a function of x, y, and z. Okay? And I can literally write that, walk around with a thermometer, take the measurements, and that's the function that describes the temperature in this room. Okay?
Okay.
All right? So that's a three-dimensional function. Okay? What happens if I also wanted to add a fourth dimension? It doesn't have to be spatial. Okay, we could use time. All right, but we could also use anything else. Depending upon what coat I'm wearing, we'll also measure the temperature of views. But with the fourth dimension will be the clothing you're wearing. Okay, that will change the temperature of your body depending upon what clothing you're wearing. So now we have 4-dimensional function, 5-dimensional. We can have any number of dimensional functions. That's all they're doing. They just simply have a function of n dimensions that describes reality. That's what they're doing. It's just an n-dimensional function that defines reality.
And it's not that little thing in the circle.
It is a little thing in the circle, but that's why they're trying to give you a visualization.
Yeah, okay.
But they're trying to give you an understanding of the universe based upon an n-dimensional, 11-dimensional function.
Thank you.
So
That's
in
really
a way,
good.
mathematics really describes or prognosticates
Prognosticates.
the universe
Oh, it does.
in ways that the actual experience of the universe doesn't necessarily.
Right, mathematics can explain things, your own experience. They then take mathematics and they try to explain it to you so you can understand it. But really, the physicists are happy with the math. They can stop there. They don't need to go into drawing crazy little things and trying to get you to believe in really thin strings and stuff. They don't need that. If the math works, they're done. Then they have to explain it to you so that you believe it too. And you don't know anything about math, so they have to explain it to you. But they believe that math explains the universe.
That's why as a little girl, if they told you you didn't need math, they cut your legs off in our era in the 50s.
Yeah. So this little business about functions is something that you learn. If you just learn about the existence of functions, which is a word you learn in high school or maybe college. If you don't take
Right.
college math, you never hear the word function. You know,
Right.
you may have heard it. This is a function of that, or you may have heard it that way. You know, but you never heard this is a two-dimensional function of that. Anyway, so I'll see you in I guess the 18th of June. Okay.
18th.
Have a good time.